Hello everyone, this is Dr. Webb and welcome to the first video for Math 235, Calculus 1. In this video we're going to be looking at functions. Now probably ever since you took Algebra 1, most of your math classes you've been focused on functions. And so in this one, this hopefully is going to be all review, but I think that it's good for us all to get on the same page with notation and terminology that we're going to be using. So intuitively, what is a function? And so normally we kind of think about functions as being sort of a black box. You stick some input into the function, and then the function spits some output back out of it. And the important part of being a function is that if I put the same input over and over again into the function, I get the exact same output out of it. So the output you get depends on the input. So if I put 7 into the function over and over again, and the first time I get 12 out of it, that means that every time that I put 7 into that function, I'm going to get 12 out of it. So some terminology we use with functions. So the domain, that's talking about the set of all possible inputs that we can put into the function. Now you also, once we start talking about domains, and you immediately start talking about ranges. And so what is the range of the function? That is the set of all possible outputs that can come out of the function. So the more precise definition of a function, using this idea of domains and ranges, is that a function is an assignment, or you can think of it as a rule, that associates everything in the domain to something in the range. And each thing in the domain is connected to only one thing in the range. And so that's how we grasp onto that concept of if you put the same thing into the function over and over again, you get the exact same thing out. So here's an example of some data. So this is just some dates and some high temperatures that we had on those dates. And so can we think about this table as representing a function? And the answer is yes, because if you look for each date, there is only one high temperature connected to that date. So the dates here, all of these dates as a set is our domain, and all of the high temperatures here as a set is the range. And so in this function, when we plug in a date, like say we plug in August 24th, then the function's going to spit out the high temperature on that date, in that case 87 degrees. Okay, now could we think about this backwards, flipping the high temps and dates? Can we think about the high temps as representing a domain and the dates representing the range for a function? Can we, if we plug in a high temp, will there be one date and only one date associated to that? And of course the answer to that is no, because if you look, 83 degrees appears in here twice. So if you had such a function, you plug 83 degrees in, how would it know how to choose between August 25th or August 23rd? So for this set of data, the only way to think about it as a function is for the date to be the domain and the high temperatures to be the range. Now for our purposes in this class, the domains and ranges of our functions will pretty much always be contained in some way in the real numbers. They're always going to be sets of the real numbers. This is really, we're going to be doing calculus on real numbers. If you keep on taking math classes, then you can start getting domains and ranges that are outside of that set. But for us, our domains are always going to be some sort of real number, some subset of the real numbers, and the ranges are as well. So our notation is usually when we're talking about a function, we'll use some letter. Typically, we'll start using f. So f will represent the function. X usually we're going to use as our variable representing the input. It won't necessarily always be x. At least in this video, it's going to be x the rest of the way. Oftentimes, we'll be using t if we're thinking about things in terms of time. There might be other variables that pop in, but x is the most typical one. And so then when we write f of x, that's representing the output we get from the function after we plug x in. So in particular, once we set some value for x, f of x is going to be that output, the value of the function, once we put that input in. So for example, if our function is you take x and then you square it, so f of x equals x squared. So what this means is that any input you plug in, and in this case the domain of this can be the entire real numbers, the output of this function is that number squared. So if we plug 3 into the function, 3 goes into x, and we square it, and what do we end up with? 9. Similarly, if we plug in minus 2, out of the function is what we get when we square minus 2, and minus 2 times minus 2 is 4. Now, something like x squared is pretty simple. What happens, the rule associated to a function like, say, sine of x, that's a lot more complicated, right? So what exactly happens when we're plugging x into sine of x? What's the rule associated to this? Well, really what's happening when we do sine of x is we're imagining some right triangle, and the measure of that angle right there is x. And so then associated to this right triangle, we have the lengths of the three sides. So we have the hypotenuse, we have the adjacent side, and we have the opposite side. And so what sine of x does is it says, okay, if you make this right triangle, where this angle right here in the bottom left is exactly x, what sine of x is it's going to be the ratio of the opposite side over the hypotenuse side. Right? And in fact, the way that often we think about this, if we're just thinking about sine, we're going to set the hypotenuse to have value 1, and so in which case sine of x for that special triangle with a hypotenuse of 1 is just going to be the length of that opposite side. And when we talk about sine of x, that is the rule that sine of x is. It's very geometric in its thinking. So typically, if you've seen, we usually like to think about graphs of functions. Why do we like to use graphs of functions? Well, if the domain of our function is the entire real line, we can't possibly set up a table of values that contains every single point on the real line. And so graphs give us some way to visualize and see the data together. Right? So when we have a graph of a function, the x-axis is representing the inputs that were coming in, so it's representing the domain. And so if we pick some x value, so let's call this, let's start calling that t. Well, then there's some point on the function, on the graph of the function, t, and then the y value there for that point is the value of the function when you plug that in, right? And so this is why we call it y equals f of x. We are setting the y values to be the outputs of the functions when you plug that particular x value into there. So if we look at y equals x squared, if I take some x value to be 1, actually let's take x value equal to be 2. We look at this point on this graph, we see that this is equal to 2, 4. And so that's telling us that f of 2 is equal to 4. So if we plug 2 into our function, we're going to get 4 out of it. Okay. If we were to plug minus 1 in, well, the graph goes through minus 1, 1, and so then that's telling us minus 1. I said it right. I didn't write it right. Minus 1, 1, and so that's telling us that if we plug minus 1 into the function's going to spit out 1. Okay, so now let's talk about some transformations of functions. So let's assume that we have some function, we know its graph, y equals f of x. Okay. So given this function, y equals f of x, how would the graph of y equals f of x minus 3 be different? Okay, and so if you notice, what we're changing is what we're plugging into the function. So instead of plugging in x, we're plugging in 3 minus x. And so what this is saying is that x is going to need to be 3 bigger to get the same output. And so if for any value we plug in, we need to make it 3 bigger to get the same output as we got before. What's that going to do, the entire graph? Well, it's going to shift the entire graph over horizontally by 3. Right? So generally, if we look at the graph of y equals f of x minus h, that h is going to represent a horizontal shift to the right. Right? So f of x minus h is what you get if you shift the graph of y equals f of x over to the right by h. Right? So let's think about what the graph of y equals x squared looks like versus y equals x minus 1 squared. So here's the graph of x squared. So then for y equals x minus 1 quantity squared, our x values have to be 1 bigger to get the same output. So every point on here is going to get shifted over by 1 in our new graph. Shifted over by 1 in our new graph. So what's it going to look like? Well, we take the whole function and shift it over. And so if you look here at, say, 2, well, so this is going to be 2, and then what happens when we plug 2 into our new function is going to be the y value. So that's 2 minus 1 squared, and 2 minus 1 squared is just 1 squared, which equals 1. And so this corresponds to this point at 1, 1 getting shifted over to the right by 1. Okay, now instead of doing a shift on the inside in our input, what if we started with y equals f of x, and then after we plugged in x, then we added 2 to our value? Right? So we plug in x into f the same as before, but then after that we add 2. Well, that means that from what we had before, every new value we would get now would be 2 bigger than before. So we're no longer shifting it left and right. We're no longer shifting it in terms of the x direction. Now we're shifting it in terms of the y direction. And so in general, if we look at the graph of y equals f of x plus k, what this is talking about is we're increasing the output by k. And so this is going to give us a vertical shift by k. So if we start off, same as before, with x squared, but now we're going to look at x squared plus 0.75, so x squared plus 3/4. Well, what's going to happen is we're going to take all of our points here and shift them up by 3/4. So every point on this graph is going to go up by 3/4. And so what it will look like, well, you just take the entire graph and shift it up. And even though it looks on the ends like things are getting close together, if you actually look at these vertical distances are actually always the same. It's always off by 3/4. And so that's what the vertical shift is going to do. Okay, finally, what if we did y from y equals f of x? What if we took f of x, and then after we plugged it in, then we multiplied it by 4? How is that going to make things look different? Okay, and so now instead of just adding by a fixed amount, now we're taking that output from the function and we're multiplying it by some quantity, in this case 4. And so what's that going to do? Well, that means that now all of our new outputs are going to be 4 times as big as they were before. So how is this going to affect the shape of the graph? Okay, and so we can kind of think about this. Usually this is called a scaling factor. So the 4 here would be a scaling factor. And so in general, if you scale a function by a factor of c, in this case I'm thinking about c being a positive number, well, if your c is bigger than 1, so that means that it's making your function bigger in absolute value, well, then it's going to stretch that function bigger. On the other hand, if your c value is between 0 and 1, well, then that's going to be making your output smaller, and so that's going to be squashing your function down. Now, if c is less than 0, then this is going to correspond to you're taking, if it was positive, you'd be making it negative. If it was negative, you'd be making it positive. And so this is going to correspond to that there's also a flip over the x-axis, because it's swapping positives and negatives. Okay, so let's try and visualize this. So again, starting with x squared, how would y equals 3x squared be bigger? Well, say at x equals 0, the y value 0, 3 times 0 is still 0. So that's not going to make any change here. Right? But at 1, 1, if we now take that y value and multiply it by 3, well, then that's going to shoot this point up to 1, 3. At 2, this is going through the point 2, 4. Well, when we multiplied 4 by 3, that's going to shoot it way off the top of this page, all the way up to 212. And so the amount of the shift, it's a scales how big that is. So the bigger the y value, even bigger the new y value is going to be. And so as you can see, here are our new functions in green. You know, when the y value is small, or in particular when the y value is 0, it's not much of a change. And when the y value is pretty small, there's not as much of a difference here. But then as the y value gets bigger and bigger of the function, the scaling gets bigger and bigger. And so that's why you can think about this greef function as it is stretching it out as you get farther and farther away from the x-axis. Okay, so last thing I want to do in this video is merge these 3 transformations together and think about how you can deal with all of them. Right, so we're going to think about what the graph of y equals 1/2 times x minus 2 quantity squared minus 1 is going to look like. So how do we deal with this? So we have both a stretch, we have a horizontal shift, and a vertical shift going on. So how do we want to piece through? And so the important thing in doing this is don't try and do everything all at once. Take it piece by piece, and you always want to start with x. What is happening to x first? So we're going to start here, and the very first thing that's happening to x is it's being subtracted by 2. And so the first thing we're going to do is we're going to do a horizontal shift to the right by 2. From x squared, x has to be 2 bigger to get the same value again. And so then we're going to get the graph of y equals quantity x minus 2 squared. Okay, and so first we have this horizontal shift going on. Okay, so now we've taken care of this part. Now what's the next thing? After we shift x by 2 and square it, what's the next thing that's going to happen to that? Well, then we're multiplying it by 1/2. Right? So this is, since it's a multiplication, this is a scaling factor. 1/2 is less than 1, and so this is going to be a squish. So we're going to take our red graph here, and we're going to squish by a factor of 1/2. And so what is that going to look like? Well, as you can see, and this is now the graph in green, we have squished it down by a factor of 2. So but from the red graph, everything in the green graph is now half as high as it was before. So whereas the red graph was going through 4 when it crosses the y-axis, now the green graph, its y-intercept is now half as big. It's 2. When the red graph was 0 at x equals 2, well, half of 0 is still 0, and so the green graph is also going through 0 there. Okay, now we don't need this function anymore. It has done its job, and so now we're focusing in on 0.5x minus 2 squared. And what's the last thing we need to do to get to our overall function? Now we need to subtract 1 at the end. And so this subtracting 1, this is going to be a shift downwards by 1 all the way across. And so the final function, we just shift everything down. And as you can see, all the way across, the difference between these, all the vertical distance between is the same, all shifted down by 1. And so we're left with, this is our graph of our final function. Right? And so remember, as you go through and do these, work from x out. So starting at x, first we did the horizontal shift, because first from x, it was then getting subtracted by 2. Then it gets plugged into the function. Then after that, then we have the scaling factor that's getting multiplied to what we get after we do x minus 2. And so that squashes things down. And lastly, we have this vertical shift subtracting by -1. Thank you. I will see you again soon.